Hi, welcome to the API in C#, the best practices of design and implementation course, where you'll learn how to design and implement robust and maintainable APIs, relying on the best practices which are tried and tested by the .NET community all over the world. My name is Elias Fofanov, aka Engineer Spock, and I'll be leading you through the course. I began my career as a postgraduate student participating in Microsoft Imagine Cup contest. I've been working with the .NET platform since 2003. I've been professionally architecting and implementing software for nearly 7 years, primarily based on the .NET platform. I'm passionate about building rich and powerful applications using modern technologies. I'm a certified specialist in Windows applications and Surface communication applications by Microsoft. API stands for Application Programming Interface. APIs are everywhere. Roughly speaking, all the functions you ever call are the part of an API. That's why it is so important to understand how to build convenient, robust and easily maintainable APIs. By the end of this course, you'll get a deep understanding of what is a good API. You'll become enough educated to reason about pros and cons of particular API design and implementation decisions. This understanding will be based on the understanding of the fundamental principles which underlie the process of designing and implementing APIs. A side benefit of taking this course is that many topics are independent of each other, what allows me to easily extend this course by new topics from time to time. I'll announce all the updates so you will never miss anything interesting. In this course, we will look at the characteristics of a well-designed API and the API development principles, how to give better names for API members and what naming conventions exist in the .NET platform and suited for C#, common problems encountered by C# developers in the process of designing and implementing APIs, classes versus structures, abstract classes versus interfaces, creational patterns versus constructors, how to implement the Dispose pattern. Are you sure you understand this allegedly simple case? Common implementation smells such as poor naming, excessively long methods, output parameters, and so on. Common architectural design smells such as primitive obsession, hidden dependencies, violation of Law of Demeter, and others. How to deal with errors. It is surprisingly hard to develop robust software where errors handling is based on exceptions. We will find out why this is so and how to struggle with problems of error handling. How to deal with nulls. Null values have always been a real pain in the ass. The null reference exception is a well-known and popular guest in our software. We will look at the possible ways of diminishing the disrupting power of null values. The goal of this course is to give you a solid understanding of the fundamental principles of building great APIs. Another goal is to teach you to build great APIs specifically in the C# language, since there are many cases specific for this language. This course is aimed at all the C# developers from beginners to seniors. Topics which are covered in the course are relevant for all kinds of C# developers, since all developers design and implement APIs. The topic's complexity is very different. There are plenty of very simple topics, and at the same time, there are topics which require from you a solid C# background. You are not forced to watch all the course sequentially. On the contrary, if you are an expert, feel free to skip the topics you understand very well. Feel free to look at the course description. I'm looking forward to seeing you inside the course. Enroll and start learning the API in C#, the best practices of design and implementation course. Hello, my name is Elias Fofanov and welcome to the course. This course will show you how to design and implement types using best practices. You'll learn how to write nice and clean code so the other developers will appreciate you, not hate you. It's very common to see unreadable, dirty, smelly code, even if the code has been written in C#, despite the power of this language. To write code of high quality, it is absolutely insufficient to learn how to use the features of C# such as lambdas, generics, delegates, extension methods, and many other. If you know how to use all these features, it doesn't mean you know how to use them properly. What does it mean? Well, the point is that most code sucks, and this is the utter truth. You definitely don't want to write code that sucks, don't you? If you want to write code professionally, then you have to understand the characteristics by which your code might be deemed as horrible or excellent. Moreover, you have to grasp many other topics except how to use a wide range of the C# features in order to produce code of high quality. So, this course is about producing high-quality code by making it simpler, logical, and extensible in the context of APIs development. You'll learn all these things in examples from the real world. I'll be your personal instructor, and I'll lead you through the whole stack of problems which you'll face in the real world. This course covers the vast majority of topics: how to give better names for API members and what naming conventions exist in the .NET platform and suited for C#. Common problems encountered by C# developers in the process of designing and implementing APIs. Classes versus structures, abstract classes versus interfaces, creational patterns versus constructors. How to implement the Dispose pattern. Are you sure you understand this allegedly simple case? Common implementation smells such as poor naming, excessively long methods, output parameters, and so on. Common architectural design smells such as primitive obsession, hidden dependencies, violation of Law of Demeter, and other. How to deal with errors. It is surprisingly hard to develop robust software where errors handling is based on exceptions. We will find out why this is so and how to struggle with problems of error handling. How to deal with nulls. Null values have always been a real pain in the ass. The null reference exception is a well-known and popular guest in our software. We will look at the possible ways of diminishing the disrupting power of null values. In this introductory module, we will talk about API characteristics, public and private APIs, and the development principles of APIs. Fine, let's move to the next lecture, where we will talk about API characteristics. One of the most popular questions on interviews for C# developers is, what's the difference between class and structure? Most interviewers expect that you'll answer that classes are reference types allocated on the heap, whereas structures are value types allocated on the stack. Most of the candidates answer exactly that. While this is mostly correct, the deeper answer is different. The main difference between structures and classes is that structures implement the semantic of copying by value, whereas classes implement the semantic of copying by reference. This is the most important aspect, especially from the API designing perspective. The only case when allocation method matters is the case of performance problems. If profiling data shows you real problems, then you might be interested in converting reference types into value types. Let's consider a good and bad examples of using structures. Let's switch to a Visual Studio and look at an example. Here is a structure named mutable, which contains an integer value. It also has a public method which increments that integer value by 1 and returns the result. This is a very bad idea, and you'll see why very soon. Consider also the following client code. We have a class named A here, which contains 3 members of type mutable. The first one is a property with getter, the second one is a public read-only field, and the third one is a regular field without any additional modifiers. In the main method, we make 3 call pairs to the increment x method for each case. What do you think will be printed out to the console? Both in the first and second cases, 1, 1 will be printed out, while in the third case it will be 1, 2. Let's explain why this is so. In the first case, we work with a property which has a semantic of returning a value. It leads to copying a new value on each call, so each call to the property mutable returns a brand new copy of the mutable structure. That's why incrementing doesn't work. The second case is the interesting one. Seems like we have a direct access to a variable here, but the thing is that compiler generates temporal variable for calls to read-only fields, so in the reality it will look like in the following code snippet. In the third case, we have a direct access to the structure instance, so in both calls we work with the same instance. Do you feel how bad the design of the structure is? It's a pure evil. This is because that structure, which implements the copy by value semantic by the language design, is implemented as a mutable reference type in the code. Let's look at a good example of a structure. Here you can see the point structure, which contains two values of type int. It exposes the increment operation, which always returns a new instance of a structure. So we don't modify the internal state of the instance, we just always create a new one. This is true immutability. It's impossible to misuse a type which is designed in this way. Mutability logically implies referential identity. Values do not have a referential identity. That's why they are called value types, not reference types. If you need to mutate something, make it a reference type. Output parameters are often used when we want to return more than one parameter from a method. Generally speaking, this is a code smell and a bad idea except for the try parse pattern, because it's widely used in the BCL and it became sort of a convention between C# developers. I've seen a great number of times code like in the following example. God's sake, this is clearly abusing of out parameters. How the hell the client's code is supposed to look like? I'm not even going to show you what it will look like, the code will just look insane. In such situation you have to refactor out all the arguments into a separate class. In this case it might be a class named Railway Dictionaries Container, which contains all the required information. As a result, the getDictionaries method would have been looked like in the following example. The second problem here is that the initial developer of this method wanted to return an error code in the case of errors during retrieving all the information. In the second version, we still return that error code as a result of the function call. How can we make this method better? In order to overcome this problem, you can rely on a result monad, which will be discussed in details in the module about errors handling. In short, the result monad is a class written in a functional style, so it allows you to store an error, a returning value, and allows you to build method chains. Look at the module dealing with errors, lectures, errors and functional programming, and pipelining by method chaining. Here I just will show you how the signature would have been look like. Do you feel how much simpler is this comparing to the first version? Let's consider another refactoring. Sometimes we just want to return a couple of values from a function, and because developers are very lazy, they don't want to create a separate structure or a class for them. Most likely, C#7 will get an improved support of so-called tuples, so we will be able to write a function with the following signature. Here's an example. Surprisingly, the caller will be able to use this function as in the following code snippet. As you can see, you get the ability to use named returned arguments as they were named in a function declaration. This is awesome! So I hope we will get this feature in C#7. This is also a great way for avoiding out parameters. Thus, strive to use out parameters as rare as possible. The most common way of using out parameters is to use them in the try parse pattern. Okay, we're done without parameters. Let's talk a little bit about comments. If we look at Wikipedia, we will see that the Law of Demeter, LOD in short, or Principle of Least Knowledge, is a design guideline for developing software, particularly object-oriented programs. In its general form, the LOD is a specific case of loose coupling. Okay, sounds great, but what does it really mean? A general formulation of the law is the following. Each unit should have only limited knowledge about other units, only units closely related to the current unit, or each unit should only talk to its friends. Don't talk to strangers. Great, sounds clearer, but still not enough practical. The formal object form of the law can be summarized as: a method of an object may only call methods of first, the object itself, second, an argument of the method, third, any object created within the method, fourth, any direct properties, fields of the object. Oh, at last the practical meaning becomes clear. Moreover, all these guidelines in the end came to the following simple statement: don't talk to strangers. Another simple formula of this law is use only one dot. Okay then, let's consider a practical example which was suggested long ago by David Bach as a great illustration of the problem. Consider the following case. Let's pretend that we should model the business relationships between a paperboy and a customer who wants to buy magazines. A paperboy rings the doorbell, a customer opens it, a paperboy somehow has to be paid, and then hand over a magazine to the customer. Let's look at the code example which models the case. Here's a simple customer class which has first and last names, and it also has a wallet of type wallet. Here you can see the wallet class. It is extremely simple. It just stores the decimal value which determines the amount of money in the wallet. The client of the wallet API can add money to the wallet, can withdraw money, and check the current amount of money. Looks good and simple. It is just fine and should fit our needs. The last thing is to implement the logic of a paperboy. Let's look inside. The paperboy class exposes a single method, deliver magazine, which takes the cost of that magazine and the customer to which a paperboy has to deliver the magazine. Looks great, let's look at the implementation. A paperboy just takes the wallet of a customer and then checks the amount of money. If there is enough money, the paperboy just takes the needed sum, otherwise a paperboy just goes away. Great, one would say. But what do you think? Is it really great? If you think a little bit deeper, then you may come out with the idea that there is something strange in the fact that a paperboy takes the wallet of a customer in order to be paid. A paperboy has access to customer's wallet. What a nonsense! Would you be so kind to give your wallet to unknown paperboys? I doubt. So, in this case, the violation of the Law of Demeter is obvious. The paperboy operates with a wallet through a customer. The first dot here in the code is when a paperboy takes the wallet. Then there's a second dot when he checks the amount of money in the wallet. The same case when a paperboy withdraws some money. To describe the problem more seriously, I should say that the main problem with this design is that the paperboy is being exposed to more information than he needs to be. All the problems are the consequences of this fact. So now these three classes are tightly coupled. If we change the wallet class, we may have to make changes to both of the other classes. By the way, if a wallet is null, then a paperboy will throw the null reference exception. So it might be that in the real-world code base, the paperboy class will have to deal with it introducing null checks and, as a consequence, cluttering the code. So, how to fix the problem? In order to fix the problem, we can just model the real-world scenario. When a paperboy delivers a magazine, he just asks for a payment. Let's look at the improved design. Now the customer class exposes a public method named getPayment, while the underlying wallet object is now contained in a private field. No one except the customer has access to its wallet. The paperboy now is forced to ask the customer to get a payment. The paperboy now does not have the rights and, by the way, the responsibility, as in the previous design, to fumble in the customer's wallet. So the improved design is better in 3 ways. First, it better models the real-world scenario. The paperboy code is now asking the customer for a payment. The paperboy does not have direct access to the wallet. Second, the wallet class can now change, and the paperboy is completely isolated from that change. Third, we're now free to change the implementation of the getPayment method. To sum up, I want to say that the rule about the number of dots sometimes can be deceitful. The thing is that the law of Demeter is not about the number of dots actually. This law is about reducing the coupling and improving the encapsulation. When we are talking about data structures, like data structures which are exposed by the Excel document, it's perfectly fine when its API allows you dig the structure of the document, like Excel document, .sheet, .cell, and so on. The same can be applied to Fluent APIs, when each call returns an object, so you can build method chains. You'll see the method chaining approach in the module about errors handling. So, as always, do not treat rules as dogmas and try to understand the underlying meaning of the rule, instead of applying rules blindly. At first, we need to understand what types of errors exist. Generally, there are 4 types of errors: recoverable and unrecoverable system errors, recoverable and unrecoverable user code errors. Let's consider them in turn. Since we use the BCL extensively, we can't evade exceptions anyway. For example, working with the file system or a network, you'll get corresponding exceptions raised by the BCL logic: file not found exception, socket exception, and many others. These exceptions are recoverable system errors, and they should be handled. It would be ridiculous if you let these exceptions to kill your application. In such a case, our application will be crashing very often. There are some kind of system errors which cannot be correctly handled. Stack Overflow exception and out-of-memory exception belong to the class of unrecoverable system errors. Even if you want to catch them, you can't do that. CLR will just terminate your application. Actually, you can catch the out-of-memory exception, but almost always you can do nothing about that. It's almost impossible to correctly handle this type of exceptions. You can't eliminate exceptions we discussed so far. All you can do with them is to handle recoverable system exceptions. Unrecoverable user code errors are the bugs in your code mostly. For example, invalid input into a function is a bug in the code, and fairly an application should fail in such a case. Null reference exception also signalizes a bug in your code, and frankly speaking, an application also should fail in this case, though we will discuss the catch-them-all approach a little bit later. The next class of errors is recoverable user code errors. This class of errors represent those errors which we expect to happen, for instance, when validation of business rules fails. C# books don't make any difference between different types of errors, so they suggest to rely on exceptions in the case of recoverable user code errors as well as in any other cases. And this is horrible. Even error codes are better than exceptions when dealing with this type of errors. Though we will not use error codes, there is a much more elegant way which we will learn a little bit later. Remember, errors are not exceptions. An exception is a form of an error representation. The original meaning of throwing exceptions is to fail fast, unwinding the stack until the appropriate catch block will handle the exception. The most important part here is the unwinding the stack. This is the main difference from returning an error. Many developers and the entire community enforces the idea that exceptions are good and error codes are bad. Also, you can hear that the following code is pure evil. Well, indeed, I agree that this exception handler looks pretty bad, but is it helpful to know only that? No, it's not. Let's consider the problems which accompany using of exceptions in the next lecture. The most common problem with nulls is that nulls make code harder to read. We tend to use defensive coding practices. We pollute the code base by all those null checks here and there. Gosh, they're everywhere. Another problem, which is connected with the first one or maybe a corollary of it, is that in the end it's very hard to control nulls everywhere, so sooner or later we end up with getting the null reference exception. The null reference exception is a real pain in the ass in every project. Another problem with nulls is semantical. Inappropriate using of nulls even makes applications design worse. Once I was reading some code in a view model and stumbled upon a method implemented as it follows. Take a closer look. This method has several drawbacks from the reading perspective, but right now I want to stress out only one. The method's meaning payload is buried inside a bad method name and the uncertainty of the following check. Look at the violet square. The overall meaning is that we have here some sort of checking the smart card. When readers look at this method, specifically at the line of the first null checking, they will ask themselves about why we have one card description passed as an argument and after that we're trying to search another card. The answer to this question, as it turned out, was that this method is performing a double check. The first argument is the description of a smart card, which has been already read in the previous step, and we're trying here to check that at the current step we're handling the same smart card, that it wasn't removed forcibly from the reading field, for example. The main problem here is that there is no strong semantic cohesion between null checking in the if statement and the logic inside that if statement. When I faced that code, I questioned myself about what did actually mean the fact that the object is actually null or not. What I wanted to say is that null checks could be completely uncertain and vague by the nature of the null as a state of an instance. Null is nothing, but what does nothing actually means? No one really knows. There are several practices for fighting with nulls. One of them is the time-honored null object pattern. This is one of the easiest ways to represent nulls. The null object pattern is about creating a special case for each type in order to represent its null state. Here you can see the diagram, which represents the design of this pattern. We can imagine almost any class as a real entity, which potentially can be null. Our goal is to eliminate nulls when working with this reference type. In order to do that, we need to extract a base class, which is represented on this diagram as an abstract entity. Please notice that we extracted the API of the real entity, which is represented by a method named doSomething. After that, we can roll out a null entity, which inherits from that base class. The implementation of the doSomething method will be empty in this case. So, when a method needs a real entity, it should require an abstract entity to be passed in as an argument. If other methods which return abstract entity need to return a null value, they will return a null entity. So, if throughout the system we use null entities instead of nulls for this particular type, then we will not get null reference exceptions. Let's consider an example. Let's pretend that we build some kind of a caching system. Here we define the iCache storage interface with three members: remove, store, and retrieve. One of the useful implementations would be the HTTP context cache storage, which caches data in the HTTP context. And here is the null object cache, which implements the same caching interface. What this implementation does? It literally does nothing. Look at the possible client's code. What might have happened if the argument of the performWork method would have been null? Null reference exception would have been thrown from the attempt to retrieve an object. Now consider what will happen if we pass an instance of the null object cache class. Nothing. Literally nothing. Sometimes this is a really desired behavior, and in such cases this pattern provides a safety net. So remember, this pattern is useful when you know that there is a meaningful default behavior. Doing nothing is a meaningful behavior in certain cases. If this is inappropriate for some reason, then it might be better to stick with nulls or implement other strategies of avoiding nulls.